is something like this. You have your inlet and you have your outlet. Later on, you will learn that for this reactor, each have their own assumption. For example, for batch reactor, the assumption is there is no flow in and flow out. And then for continuous tank reactor, the assumption is this will be well mixed because it will be well stirred, and this also will be well mixed. And the other part is because the flow rate is constant, so the volume is also constant, and this one is also constant. Later on we will see. But for this one plug flow reactor, there is some difference where later on you will see they will involve changes in volume, because in this phase and this phase there will be some difference. Later on we can see. And same with packed bed reactor. Pack is on this reactor will be filled with some material, whether it's adsorbent or catalyst or something else. And other type of reactor is fluidized bed reactor and trickle bed reactor. Okay, here is some examples, some more example of ideal reactor and real reactor in industry. Typically, we want to have a ideal reactor because they are well mixed, there is constant rate, and some other factor. And this is the real reactor is derived from the concept of ideal reactor. So it's either batch, continuous, or plug flow. For a batch, there is no flow in and flow out. And then the concentration is depending on time for batch reactor. Ada siapa-siapa yang belum masuk? Tak ada. Okay. Another aspect that you need to know for this topic is conversion. We denote as X. So because in the reactor, normally we used to convert reactant to production. So we need to quantify with the product with conversion. So what is conversion? Conversion is how far the reaction has progressed. So we can, the formula is this, which is S mole of species reacted over mole of species in. Okay, mole of species reacted, which is the changes between mole X at certain time. Initial minus mole initial minus mole at being changed, so you will get mole of species reacted over mole of species being fed, which is the initial mole. So the conversion for each reactor is different. For example, for batch reactor, the conversion is number of initial mole minus mole of reacted over initial number of mole. And then for continuous or flow reactor, the conversion is initial mole flow, which is mole flow in, minus mole being converted over initial number of mole. And then this will be mole per hour, mole per liter per hour. While this is just in concentration unit. So make sure you you get the definition of conversion and identify the difference between batch reactor and continuous reactor. What is this? Okay, the conversion of a reactant in chemical reactor is related to time that the chemical species spend in the reactor. So two type of time parameter are commonly used in chemical engineering reaction. The first one is space time, and the second one is residence time or contact time. So these two parameters will determine how big is your reactor. So space-time is often used as scaling parameter in reactor design. So what is space-time? So space-time is time required for one process in reactor volume at inlet condition to finish. So the definition space-time is volume over volume charged to the reactor per second. So meaning that how long is the time required for one volume of inlet to finish lah. While for space velocity is we denote as SV is equal to V naught over V. So it's the opposite of this one. So it can be liquid hourly space velocity or gas hourly space velocity, depending on the phase of the reaction. And residence time is the actual time spent by fluid, which is the feed, inside the reactor until it being converted into products. Okay, general material and energy balance. The starting point for the design of any type of reactor is general material balance. So you need to know the amount of inlet should be equal to the amount of, not really, there will be this assumption, this one. The material balance can be carried out with respect to one of the reactant or one of the products, but normally we will consider the reactant. Basically, the general material balance for a reactor follow the same pattern as all material and energy balance. So this is the general material balance, which is the input is equal to output plus reaction plus accumulation. So the input is normally the F FA naught. The output is FA. The reaction is depending on the reactor, and accumulation is also depending on accumulator reactor. For certain reactor, they won't have certain criteria or parameter, so this can be cancelled out. So the derivation will be different. Later on, you will see. Okay, material balance in consideration of volume. In setting out the equation in exact form for any particular reactor, the material balance can be carried out over a certain element of volume or over a certain element of time. So the rate of flow of reactant into volume, which is the element 1, is equal to rate of flow of reactant out of the volume, which is the element 2, and then rate of reactant removal by reaction within volume plus rate of accumulation of reactant within the volume element. So this is similar to this one. This is more simple if you guys want to remember. This one is more simple. So for each basic type of chemical reactor, the material balance equation may be simplified. For batch reactor, term 1 and term 2 are 0 because there is no flow in and there is no flow out. So for batch reactor, this 2 is 0. And the rate of accumulation, for example, the rate of disappearance of the reactant is equal to the rate of reaction. So that's why they are in equilibrium for batch reactor. However, for continuous stir tank reactor, if operating in a steady state means that the flow steady in and out is the same, so they are in steady state. So the rate of accumulation and term 4 is by definition is 0. So this one will be 0 because there will be no accumulation. And the rate of reactant removal by reaction is balanced by the difference between inflow and outflow because they are in steady state. While for heat balance is similar. Input is equal to output plus reaction plus accumulation. This one is similar. Material and heat balance is similar. Please remove. What is this? Wait, Okay. Now let's look at the first type of reactor, which is the batch reactor. So this reactor is very simple. So it is closed system, unsteady state of operation because there is no flow in and flow out. So there is no spatial variation of concentration or temperature. So we assume that they are homogeneously mixed well. And it's mainly used for a small scale operation and is suitable for slow reaction. Because later on you will see the comparison batch, flow and plug-in. Batch is require longer time compared to flow and also compared to plug-in. And mainly used for liquid phase reaction and it's easy to clean out. The advantage of batch reactors are small batch reactor require less supplementary equipment such as pump for the continuous reactor. Control systems are less costly because you just need to monitor the temperature. Interval between batch provide opportunity to clean the reactor. For example, in polymerization or fermentation. And then prevent batch mix problem and typically used in heterogeneous reaction. An agitator can be designed to suspend solid in the liquid. And for batch reactor, the characteristic is the reactor is charged via, no, it's similar. You can just read this. You can just read down the advantage and disadvantage. And this is the general material balance in batch reactor. So typically, for general material balance, imagine this is inside the reactor. Supposedly, you will have a input gun. This is input is equal to the output plus reaction plus accumulation. So you can write down like this: input minus output plus the derivation of reaction rate in terms of volume, and then at the end you will get DNA, this is the number of mole over the. So the assumption in a batch reactor is that there is no flow in and flow out. So FA is equal to, FA naught is equal to 0, so FA is also equal to 0 because there is no flow in and flow out. So the simplified form of the derivation equation for general batch reactor is dNA over dt is equal to the integral of reaction rate times volume. However, because in batch reactor they are well mixed, so we can ignore the volume. So we can simplify this, and this is go out. So you got RA, the integration of dV. So at the end you got this. So remember, for batch reactor, the general mole balance is this one. dNA over dt is equal to rate of reaction times volume. Because in a batch reactor, there are constant volume as well, because there is no flow in and there is no flow out. So the volume is constant. And typically this is in liquid phase. So we can write down that the dNA over VO, this is the concentration, over dt is equal to RA. So the concentration is equal to rate of reaction. Then, because in reactor is involving with conversion, we need to integrate with conversion. So we already know that the conversion in batch reactor is the changes of mole of the reactant being fed, which is the NA naught minus NA over NA naught. So the changes in concentration over concentration or mole is the same over the initial number of mole of reactant being fed. So we arrange this. We know that the number of mole being, the changes of number of mole is equal to number of mole, initial number of mole minus, minus number of mole being converted. So we can simplify this as number of mole NA naught 1 minus x, 1 minus x. And then you can substitute this into the dNA over dt, then you will get this. You substitute this into this, and then you will get this. And finally, the dx over dt is equal to negative RA times volume over initial number of mole. And then when you integrate them, you will get this simplified form. T is equal to integration of dx over negative RA times V. Okay, this is typically the order reaction for batch reactor. So you can use hour, minute, second, or millisecond. So for first order reaction, the typical unit is second -1 . And for second order, typically is, what is this? S -1. This is the reaction rate, KCA naught, and then this is K. And this is the table showing the various time necessary to process one complete batch. So for a batch reactor, we know that the mole balance is this one. dx over dt is equal to rate of reaction over initial mole times V. So remember this. For first order, we know that the reaction rate is equal to KCA because it's involved with the concentration. This is for first order. While for second order, is the reaction rate will increase with increasing of concentration. So reaction rate is equal to Kc cube square. So when you combine them, you'll get this. And typically for a calculation to determine the time required, you guys can normally will use this. For example, a question will ask you, what is the time required to convert this amount of products to this one? And then they will give you the rate constant and then the conversion. So you need to find the time so you can use this. Depending on the order of the reaction. This is the first order, this is the second order. Okay, this is some example. The question asks you to calculate the reaction time for aqueous reaction of A to B. That process 500 liter feed volume of 5 molar A in a batch reactor. So it's batch reactor. Given that the conversion is 90% and the rate constant is K. So you can use this to find the time. And you know K is 5 and the conversion, the X is 0.9. So you need to find the time. So you just substitute into this one. So you can try this on your own. Okay, that one is for batch reactor. Now let's look at for continuous stir tank reactor, which is CSTR. So we know that for stir tank reactor, we have a mole flow in, which is FA naught, and also we have flow out, which is the the products. So the assumption in continuous stir tank reactor is it is steady state operation because there is a flow in and flow out, so it exists in steady state. And it also can be used in series, meaning that they can add another one reactor here. So it will be in series form. So there will be no spatial variation of concentration or temperature. So we also assume that they are well mixed. And then mainly used for liquid phase reaction and suitable for viscous liquid. So the basic assumption are the content of the tank are well mixed. And then the composition in the tank are uniform everywhere. So the product stream leaving the tank has the same composition as the mixture within the tank. Then the mass density of the reaction mixture is constant. So these are some advantage and disadvantage. The advantage are it can be used in continuous operation, so they can use in a series of reactor. They can combine them. They also have good temperature control, easily adapt to two-phase run, simplicity of the construction, low operating costs because they are automated and because they can keep fed in the reactant. While for batch reactor, you need to put the reactant, and then after finish, you have to top up it again. While this one is automatic, and it's also easy to clean. However, the disadvantages are lowest conversion per unit volume, and bypassing and channeling possible with poor agitation. Similar, this is the diagram for continuous batch reactor. And this is the general mass balance. So remember we have the input is equal to the output plus the reaction plus the accumulation. So we have FA naught minus FA plus the reaction rate is equal to dNA over dt. And we know that in continuous reactor, they are steady state. So therefore, the dNA over dt is equal to 0. Because we don't consider the time because they are in steady state. So well mixed, they are therefore reaction rate is the same throughout the reactor. So we can just ignore this because the dimension is similar because they are in well mixed can. So everywhere in this reactor is homogeneous. So the rate is the same throughout the reactor. So finally we arrange this, we got this. The rate of the reactions is equal to this one. And then we rearrange it again in terms of volume. We got that FA naught minus FA over negative reaction rate. And then in terms of conversion, we know that the definition of conversion for continuous reactor is this kind: flow in over flow out over flow in. And similar with it, we know that FA is equal to FA naught minus FA naught X. This is the changes in concentration of the reactor. So you got this one from here. And then finally you get this. Because you substitute FA with this one. So you got this. Since FA naught is equal to V naught times concentration at A naught, you can rearrange this, substitute the definition of FA naught. With this one, you got this, where VO is the volumetric flow rate. So in relation with the space-time, time required to process 1 reactor volume of fluid at inlet condition, we know that space-time is volume over V naught n. And then we rearrange with this. We got this. This is, for example, at constant volume. The concentration of initial inlet stream is equal to this one. Ca is equal to Ca naught times 1 minus x. 1 minus x is the amount of being converted. So we substitute for T here, this Ca, then you got this. So similar with batch reactor, we have first order and second order. So for example, first order A is reacted to form B. We have a reaction rate is equal to Kca. And we know that Ca is equal to Ca naught minus Kca time space. And then to obtain the time space, we can use this formula. For second order, it's similar, it's just that the concentration is double because we have 2A react to form B. Similar, if you want to find the concentration being converted, here we solve this equation, we got this. Okay, flow reactor. Okay, the flow reactor is chosen when it is desired to operate the reactor continuously but without back mixing of reactant and products. An ideal flow reactor, the reaction mixture passes through in a state of plug flow, which the fluid moves like a solid plug or piston. So the volume will move constantly. So for ideal plug-in reactor, the local mass flow rate, the fluid properties and temperature, pressure, and composition are uniform across any section, normal to fluid motion. So all elements of fluid take the same time to pass through the reactor and experience the same sequence of temperature, pressure, and composition changes. So in calculating the size of reactor, for example, we consider the volume. So shape does not affect the reactor as long as plug flow occurs. So plug flow is this one. We have flow in and flow out. But we assume that in every section, the movement is constant. So we consider this. So there will be a difference in volume. The flow pattern of fluid will determine the shape of chosen for a reactor. So factor to be considered in plug flow continuous reactor is whether plug flow can be attained, heat transfer requirement, whether there is pressure draw or not, support of catalyst, easiness and cheapness of construction. Okay, plug flow or tubular reactor consists of hollow pipe or tube through which reactant flow. So the reactant will flow inside this. For example here, plug flow reactor in the form of tube wrapped around acrylic mold which is encased in a tank. Water at control temperature is circulated through the tank to maintain the constant reactant temperature. So plug flow reactor is also known as tubular reactor, which consists of cylindrical part with opening on each end for reactant and product to flow through. So they can exist in many forms, whether in cylindrical or tube. Tube is like this, and this is cylindrical. And then plug flow reactors are usually operated at steady state. similar with the continuous, because plug flow is also continuous, so they are steady state. And reactants are continually consumed as they flow down the length of the reactor. So it's not like a batch. Batch reactor, the limiting step is the reactant, because there is no flow in back. For equipment design, plug of reactant are continuously fed into the reactor from the inlet. As the plug flow down the reactor, the reaction takes place, resulting in axial concentration gradient. Product and undirected reactant flow out the reactor continuously. Later on, we can see what is the axial concentration gradient. This is the concentration gradient. So you have the fat in here, and then this will be the products. Because the mixture move in axial flow like this, so in each segment there will be different concentration. For example, this will be full of reactant, and this will be less of reactant and more product. So the gradient, concentration gradient is different, but they consider it in this segment, like this segment. Changing of concentration. Okay, plug flow reactor are configured as one of the long tube or a short number of tube. So they can be long or short depending on the reaction. So the choice of diameter is based on the construction cost, pumping cost, and the desired residence time and the heat transfer needed. Typically, long, small diameter tube are used with high reaction rate, and larger diameter tube are used with slow reaction rate. The application for plug flow reactor, they are widely used in gas or liquid phase system. Common industrial use of tubular reactor are in gasoline production, oil cracking, synthesis of ammonia, oxidation. This is another example. This reactor is being used in oxidation of nitrogen compound, and it can reach up to 800 to 1100 degrees Celsius. Here another example. This plug tube reactor is being used as bioreactor for small scale production. The tubular bioreactor shown below is used for the production of algae. The algae is then compressed and dried and can be used as feed for biodiesel reactor. Okay, here are the material balance for plug flow reactor. I don't know why is this one. So we know that the schematic diagram of plug flow reactor is like this. So the assumption involved is it is steady state operation, and then partial variation in axial direction, but not radial direction. So suitable for fast reaction, mainly used for gas phase reaction. Temperature control may be difficult, and there are no moving parts. So there is no agitation because they just flow here. Now let's look at the advantage and disadvantage. It is high. It can be used for high conversion per unit of volume, low operating costs, continuous operation, and good heat transfer. And the bad side is the undesired thermal gradient may exist, poor temperature control because there is no agitation, and shutdown and cleaning may be expensive. This one you just have to identify, differentiate the which one is the advantage and which one is disadvantage. Okay, this is the mass flow for plug-in reactor. Since the composition within the reactor is varies, we take a balance over a differential element of volume. So we have FA naught, which is the inlet, and we have the FA, which is the products. From here to here, we have the changes in volume one. For example, in batch reactor, we have the function of temperature, but for plug flow, we have the volume parameter, the changes in volume. So from here to here, the difference is just that FA, this one is FA function of Y, this is FA Y plus delta Y. So same mass balance assumption, in minus out plus generation is equal to accumulation. So here is the basic equation. Similar here. In, out, direction, and the accumulation. But because the assumption as it is steady state, this one is equal to 0. And then after we differentiate, we got that dNA over dt is equal to 0 because there is no accumulation. We differentiate it, we got dFA over dV is equal to RA. So it's similar to the continuous flow reactor. We have this for conversion. At the end, we got this similar with the action for plug flow reactor design equation. So when you want to design the reactor, normally you will use this equation because from here you can get the volume needed and also the time space for the reaction. So here you have dFA over dV is equal to RA, and we know that the changes in mass flow, which is the mass flow in and mass flow out, is equal to this. We arrange this, we got this one. And then similar, we substitute this and we got this. And this is bed reactor. It's similar with the plug flow, but we have something that you put inside it here, whether it's a catalyst or adsorbent. The assumption is similar, steady state, partial variation, but no temporal variation, mainly used for gas phase catalytic reaction, although example for liquid phase reaction also known. There are no moving part and pressure drop across the pack. That is important consideration. And here is a cross diagram of the fixed bed reactor. The difference is that you have this bed. Okay, here is another example involving. Sorry, this one is disturbing. Okay, problem 1. An irreversible second order reaction. So the dimension is a second order. A to B take place in a plug flow tubular reactor. So derive the equation to determine CA, starting from the following equation. So basically, you just need to solve this, to solve CA in this equation. And then for B, using the derived equation, determine CA if CA naught is 2.0 mole per liter, and reaction rate is 0.05 liter per mole times S, and the space time T is 10 minutes. And then calculate the conversion at space time 10 minutes. And finally, calculate the time required for the reaction to reach 99% conversion. So let's look at, later on we will look at this solution. And problem 2 is calculate the reactor volume for aqueous first order reaction A to B first order that process 1000 liters per minute of 5 molar A in plug flow tank reactor and CST continuous tank reactor. Given the conversion is 80% and the rate constant is 5 minutes. So here is the solution. So here is the equation given again. So you just rearrange this to solve CA. So it's just all mathematical equation. You solve this here, and then you got this, simplify them, and then finally you got this. So once you solve this, you can find the concentration CA when the initial concentration is given 2.01. Just substitute all the information, and then you got the answer. And then the conversion, you just substitute all the information. Conversion at this time is this, and we got the answer. For D, concentration as conversion of 99%. So you always write X as 0.99, and then you substitute in this formula. So yeah, this is 1 minus X. And then put it back in this equation, we will get the space-time. And then this is for solution of example 2. You need to find the concentration at 80% conversion. So again, you remember this formula. This is the first order. And then you solve this, you got 1 mole. And then for time space, just use this formula, and you got the answer. Similar to this is plug flow, this is continuous stir. There is different plug flow and continuous stir, the formula is different. And then you got the answer. Okay, that's it for ideal reactor. I will upload more content. Maybe I will upload the equation involved and also the formula, so that you can learn how the derivation of each mole balance. Okay, guys, understand? Are you guys there? Any question?
No.
So basically, for